All right, guys, in this video, I'm going to be going over AP Chemistry thermodynamics quiz. So just a practice quiz, different thermodynamic questions you might see on the AP exam, and this is going to strictly focus on multiple choice problems. So this is just a thermo practice quiz, mainly focusing on delta G, delta S, and delta H. And then obviously temperature is always a factor when you're dealing with thermodynamics. So we're just going to go through the quiz and talk about the different things you should be thinking about and what the right answers are as we go through it. Okay, so first, so let's look at the quiz. So the quiz says entropy and free energy, but you're also going to need to know enthalpy, so delta H as well. So remember, entropy is S, or the change in entropy is delta S. Free energy is G, or the change in free energy would be delta G. And then also for thermodynamics, you got to think about enthalpy, and that's delta H. Change in enthalpy is delta H. And also T, temperature. Okay. And then notice on this quiz, you are given the standard thermodynamic equations on your AP chemistry sheet. But notice like this section here doesn't have the R values. On the actual AP chemistry formula sheet, you're given the R values. So we can go to the actual formula sheet for the AP exam and notice you got your thermo equations. And then notice you also have the R values. And whenever you're dealing with thermodynamics, especially these equations that have R in them here, this one, the R value in question is this R value. So, you know, this R value here you tend to use with the ideal gas law, same with this one. This R value you don't really use with the ideal gas law. This is for thermo and electrochemistry. But in thermo, you know, notice the delta G equation where it says delta G equals negative RT natural log of the K, the equilibrium constant. The R value you would plug in if you use this equation. And what you're going to find out is we're going to have to use this equation on the quiz. The R value we'd be plugging in is this one, the 8.31. Okay, so let's go in and look at the quiz. But before we look at the quiz, there's a lot of things, a few things that you just really need to just know. And just like if you're told X, then you know what, you know Y, W, and Z, right? If you know that this is true, then if A is true, then B, C, and D are also true. There's a lot of questions that you can answer in AP chemistry, especially when it comes to thermodynamics and equilibrium and electrochemistry, where if you just know the algebraic sign for one of these things, delta G or delta S or delta H, or the value of the equilibrium constant, if you know one of those little things, you know a lot about all the other things. All right. So again, if we look at this practice quiz, the main focus is entropy and free energy, but enthalpy, delta H comes a long way. So before we dive in the quiz, things we want to know a little bit more. Let me just organize this a little bit better. So again, this equation means a lot to us, but before we start talking about this equation, in AP chemistry, the word spontaneous means thermodynamically favored. And it used to, like, old school AP chemistry, we would say spontaneous or not spontaneous. Understand new school, instead of saying spontaneous or not spontaneous, we're going to say thermodynamically favored or not thermodynamically favored. Okay? And one thing you need to understand is if you're asked if a process is spontaneous or not spontaneous, or thermodynamically favored or not thermodynamically favored, if that's the question you're asking and you have to justify, you can justify this one of three ways. You can talk about the sign of delta G, the sign of cell potential, or the value of K, the equilibrium constant. So because we're dealing with thermo in this question, or in this quiz, what we really need to know is a negative delta G, any value, a negative delta G. If it's negative, the reaction's spontaneous at that temperature. A positive delta G, the reaction's not spontaneous or not thermodynamically favored at that temperature. Okay, and then also understand when delta G equals 0, that means one way to interpret delta G being 0 right now is that you're at equilibrium. But another way to interpret delta G equals 0 is that both the forward and the reverse reaction are equally favored at that temperature. Or a better way to think about it is when delta G is 0, whatever that temperature value is, where delta G for a reaction is equal to 0, then that's the temperature tipping point where anything above or below that temperature, the reaction becomes more or less spontaneous. And whether it becomes more or less spontaneous as temperature increases really depends on if it's an endothermic reaction or an exothermic reaction. So it really depends on the sign of delta H. Is it positive endothermic or negative exothermic? But right now, if you're just asked if a reaction is spontaneous and you have to justify it, well, figure out what delta G is. If delta G is negative, then you can say it's spontaneous. If delta G is positive, you can say it's not spontaneous. But the other two values you could use to justify if a reaction is thermodynamically favored at a given temperature or spontaneous is the value of K and cell potential. Now, since we're doing a practice quiz on Thermo, cell potential probably has not been taught to you. So you can kind of ignore this, but you most likely have talked about the equilibrium constant. So another thing to a quick tie-in to understand about this is anytime delta G is negative, that means the equilibrium constant is greater than 1. Because an equilibrium constant being greater than 1 means the reaction is thermodynamically favored or spontaneous. Okay, so a negative delta G means the equilibrium constant has to be greater than 1. Okay, it also means the cell potential is positive, but we don't have to worry about that right now. Okay. A positive delta G means at that temperature, the reaction is not spontaneous, and that would mean that the equilibrium constant is less than 1, okay? And that would mean that the cell potential is negative. But again, we don't have to worry about cell potential. But just a quick tie-in. As soon as you know you have a positive delta G, you know the reaction is not spontaneous, and you know the equilibrium constant is less than 1. As soon as you know you have a negative delta G, you know that the reaction is thermodynamically favored or spontaneous, and you have a KEQ value greater than 1. Okay, so those are just a couple of tie-ins. Okay, and then also understand how delta G depends on the delta H value, the delta S value, and the temperature value. And if we think in terms of algebraic signs and how this equation would work, and what a negative delta G means versus a positive delta G, okay, and we'll see this throughout the practice quiz. We'll see some examples of this. Okay, but if you have also understand this has to be the Kelvin temperature that you plug in here, and Kelvin can never be negative. So you know that this value is always positive. The T value you plug in here is always positive, okay? So knowing that, that means if you have a negative delta H, so if this value is negative, and you have a positive delta S, that means this value is positive. If your reaction has a negative delta H and a positive delta S, it doesn't matter what you plug in for the temperature value on the Kelvin scale, which is always a positive value. If this value is negative and this value is positive, no matter what you plug in for the temperature, this equation is going to yield a negative delta G. So what is that telling you? It's telling you when delta H, when a reaction is exothermic, but it also has a positive delta S, which means it increases in entropy. If you have a reaction that's exothermic with an increase in entropy, the reaction will always be spontaneous no matter what the temperature. You will always end up with a negative delta G. Conversely, if this would be positive and this would be negative, then no matter what you plug in for temperature, delta G would come out to be positive and the reaction would never be spontaneous at that temperature or at any temperature, okay? So that leaves the usual suspects, the negative or positive combo. So if you have a negative delta H and a negative delta S, and that's usually when delta H is negative, you usually have a negative delta S, and if delta H is positive, you have a positive delta S. Usually it's a negative combo or a positive combo, but not always, okay? Okay. But if you have a negative combo, the sign of delta G is going to depend on the temperature. And if you have a positive delta H, delta S combo, the sign of delta G is going to depend on the temperature. Okay. All right. So just remember, a reaction can be favored in terms of entropy change, and that would be a positive delta S, or a reaction can be favored in terms of enthalpy change, and that's a negative delta H. So if a reaction is favored, meaning if a reaction has a negative delta G, but it has a positive delta H, that must mean it also has a positive delta S, and what's driving the favorability of the reaction is the entropy change. If delta G for a reaction at a given temperature is negative, and you have, let's say you had a negative delta S, then that means the enthalpy change must be a negative delta H, and the reaction's being driven spontaneously because it's enthalpically favored. It's favored in terms of the enthalpy change. Okay. When you have this combination, a negative delta H and a positive delta S, the reaction's always favored because it's both favored in terms of entropy change and enthalpy change. Okay. So if a reaction has a positive delta S and a negative delta H, the reaction will always be favored no matter what the temp, right? And that's just using this equation. No matter what the values are, if this is a negative and that's a positive, delta G, in whatever numbers you plug in for this equation, knowing that temperature can only be a positive value because it's the Kelvin scale, delta G is always going to come out to be negative. And a negative delta G means a spontaneous reaction. Okay. So again, negative delta S, negative delta H, positive delta S, always favored. When you flip that and you do a negative delta S and a positive delta H, so a positive delta H and a negative delta S, delta G would always come out to be positive there, so never spontaneous. Okay. All right, so now let's get into the practice quiz. All right, so we go to question number 1. All right, so question number 1, it says, which of the following represents an increase in entropy? So we're looking for an increase in delta S, so a positive delta S, which means an increase in randomness for disorder. So the products have to be more random than the reactants. That's what we're looking for. So if we look at my notes, I'm going through each process. So liquid to solid, that's going to be more ordered, so that would be a negative delta S. Liquid to gas, that would be more, gas particles are more disordered than liquid particles, so that would be a positive delta S. The precipitation of sodium chloride, so aqueous ions to form solid. Aqueous ions move around, so they're more random than solid ions that are stuck in a fixed position. So ions precipitating out of solution, that would be a negative entropy change. 2 moles of gas particles to 1 mole of gas particles. Less gas particles would be less random, less disordered, so that would be a negative delta S. And notice here we have 3 moles of gas going to 2 moles of gas. So again, less gas particles, that would be a decrease in entropy. So the answer to number 1 would be B, okay? The boiling of water, because we're going from, the boiling of water would be liquid to gas, all right? All right, so let's go to number 2. It says the enthalpy of vaporization for methanol, so the delta H is 35.3 kilojoules at the boiling point. So here's the thing where you need to know. At the boiling point would mean that's the temperature with delta G equals 0. Because at the boiling point is also the point of condensation. So you could be talking about vaporization or you could be talking about condensation. And the boiling point is the temperature where both are equally favored to happen. So that's telling you the delta G is 0. And so it's saying, here's the delta H, and that right there is cluing you in that the delta G has to be 0. And so it's saying calculate the entropy change. And so that's just using our equation, but this is where we have to be careful about what we were given, okay? So again, we were given the molar heat of vaporization of methanol, so that's just liquid methanol yielding vapor methanol. And we know the delta H was positive 35.3, okay? Now we're using this equation. We know the delta G, we know the delta H, we know the temperature, right? They told us the temperature was 64.2. So we're just solving for delta S. That's what we're solving for. But this is where we got to be careful, okay? Notice the S's, and this is the normal, this is usually how it is. Entropies are usually in joules, okay? But delta H's are usually in kilojoules. So when you plug them into that equation, you got to make sure you're either all in kilojoules or you're all in joules. So since we're solving for delta S and all the answer choices are joules, I'm going to convert the kilojoules delta H to joules before I plug it into this equation. So I'm going to plug in 0 for the delta G because we're at the boiling point, and so that means at that temperature delta G is 0 because both the forward and the reverse reprocess are equally favored at the boiling point. But notice I didn't plug in 35.3, I plugged in 35,300 joules, okay? And then the temperature, notice I didn't plug in 64.2 or whatever it was. Yeah, 64.2, I didn't plug in that. It's got to be the Kelvin scale. So you got to add 273 to your Celsius. So that's where that number came from. And then we just solve for delta S, okay? Another thing to understand is we should be expecting delta S to be positive because liquid to gas would be an increase in entropy. So I forgot to do this, but notice like on my annotated quiz here, I crossed out D and E right away because I know that delta S would have to be positive in this case. So I know it's not D or E. So if I had to guess, I'd guess A, B, or C, okay? But, you know, you can actually just plug in and solve. So when you solve, delta S comes out to be around 105, and so our best answer choice is C there. Okay, so as we go to number 3, it says calculate the standard entropy change given this equation and given the entropy values for the different parts of that reaction. So remember, you have this equation on your formula sheet right there. The delta S of the reaction equals the entropy of the products minus the entropy of the reactants. Now what you have to do is notice the entropy values given to you are per mole of the substance. And remember, the coefficients represent the moles of each thing. So for like when you're using the entropy of O2, you got to multiply it by 1/2. You always have to multiply by the coefficients in your equation when you're plugging into that equation. So for the copper and the copper oxide, we don't have to multiply by anything. We can just use the values that were given here for those. But for the oxygen, we're going to use half of this value. Okay, but it's products minus reactants for the delta S of the reaction. Okay, so we're just plugging in the values that we were given. Okay, we only had one product, and then these were our reactants. But notice for the oxygen, I multiplied it by 1/2 there. Okay, and we solve. Okay, now another thing to look out for is, you know, we had a solid and a gas going to one solid. So since we had gas on this side and only solid on that side, that's going to be a decrease in entropy. So we should be expecting a negative delta S, right? So I didn't do it here, but I should have like looked at this knowing it going in that the sign of delta S would have to be negative. So I would cross out E, A, and B as possible choices. It would have to be C or D because I know delta S would have to be negative. I wrote it here, but I didn't cross out the ones that would negate. Okay, so when we do the math, when we plug it into that equation, we get negative 93, and so D would be our answer choice there. Okay, so moving on to question 4. In which of the following reactions do we expect to have a decrease in entropy? So basically, we're just looking at states of matter, knowing that solids have less entropy than liquids, liquids have less entropy than gases, and then if you look at aqueous ions have more entropy than solid ions in a solid, right? So those are the things. And so what a decrease in entropy is, you want your products to be less random than your reactants. That would be a decrease in entropy. Or you're looking for more ordered or less disordered products, all right? So solid to liquid, that would be an increase in entropy, so we know it's not that. Here we have solid to solid, so that could be a choice, okay? That could be a choice. We're not sure yet, but we have solids on that side and solids on that side, so maybe that's going to be a decrease, but maybe we'd have to know more about it. You know, so this might end up being more disordered. This, we're not sure yet, okay? But if we look at C, we have 2 solids, but we also have 3/2 gas going to nothing but solid. So C is definitely going to be a decrease in entropy. D, definitely not. That's an increase in entropy. And also E, we got liquid, only liquid, and then we got liquid and gas. That's going to be an increase in disorder. So the answer is going to be C. It's going to be, you have gas on one side, solid on the other. That's definitely a decrease in entropy. Okay. All right, so we keep on moving. We'll go to number 5. So number 5, it says the formation of this compound has an enthalpy formation of negative 104 and an entropy change of negative 60, 60.8. We want to know what is the delta G and spontaneity of the reaction. So this is where we're going to plug our delta H, our delta S, and our T into the delta G equation, and we're just looking to see if delta G is negative or delta G is positive. If it's negative, it's spontaneous. If it's positive, it's not spontaneous. That's it. Okay? Now, let's go ahead and eliminate the answer choices that don't make sense, right? If this is delta G, if it's a negative value, then the reaction is spontaneous. So you can't have a negative delta G and it's say not spontaneous. So B doesn't make sense. You can't have a positive delta G and the reaction be spontaneous. So C doesn't make sense. And then E doesn't make sense again either, because if you had a negative delta G, it would be spontaneous. It wouldn't be not spontaneous. So E doesn't make sense. So by just process of elimination, B, C, and E don't make sense. Okay? So the only two possible choices could be A or D. It's either the reaction, delta G comes out to be negative, so the reaction is spontaneous, or delta G comes out to be positive and the reaction is not spontaneous. That's what you have to figure out. Okay? So, students just mess up a lot. It's very simple algebra, but where they mess up is a lot of times they don't change the units, right? Delta H was given us in kilojoules, and so notice I changed it to joules, multiply it by 1,000, okay? And the temperature I was given was in Celsius. I got to convert that to Kelvin, okay? All right. Now, I could have taken my, and I probably should have. I probably should have kept this as negative 104, and I should have converted this to negative 0.0608 and put this into kilojoules instead. So my final answer would come out to be kilojoules, because notice the answer choices were all kilojoules. Okay, I didn't. I usually convert to joules, so that's what I did here. So I got my delta G in terms of joules, and then if you divide that by 1,000, that's the kilojoules. Okay, and so it came out to be negative, and that means the reaction is spontaneous, and so our answer is A. Okay, but kind of understand how you can, a lot of these questions you can eliminate a lot of answer choices. So if you just had to guess, you could turn a 1 in 5 chance into a 50-50 shot here, knowing that B, C, and E didn't make any sense in terms of logic, right? Okay. So if we go to number 6, if delta H and delta S are both negative or positive, then delta G is variable. Remember, the only time, so the times where delta G could be negative, could be positive, depends on the temperature, is when you have a negative delta H delta S combo, or a positive delta H delta S combo. If you have a negative positive combo, it's either always spontaneous, so always negative, or never spontaneous and always positive in terms of delta G. Okay, so when you have a negative delta H delta S, or a positive delta G is going to depend on temperature. So it's going to be, the sign is going to be variable depending on the temperature. Okay. All right. So again, and what you should understand moving forward also is, if you do have a negative combo, understand, so that means it's an exothermic reaction. That reaction is going to become less favorable as temperature increases and become more favorable as temperature decreases. So when you have a negative combo, delta G is going to increase as temperature increases. Now understand what that statement's saying. If we're saying delta G increasing, we're saying the reaction becomes less spontaneous as temperature increases. So when you have a negative combo, delta G is going to start to increase as temperature increases. The reaction becomes less favorable as temperature increases when you have an exothermic reaction in a negative combo. When you have a positive combo, when your reaction is endothermic, a positive delta H, then delta G will decrease, meaning the reaction will become more spontaneous, more favorable as temperature increases. So heat or temperature, increase in temperature favors endothermic reactions. It doesn't favor exothermic reactions. Okay? So just another thing to understand. Okay? All right, so number 7, at what temperature would a given reaction become spontaneous if delta H is positive 119 and delta S is positive 263. So this is a positive positive combo. So the reaction is going to become more spontaneous as temperature increases. But they want to know at what temperature will it become spontaneous. So they want to know the temperature tipping point, and that's where delta G equals 0. So you want to know what is the temperature where delta G equals 0, and then anything above that temperature for this combination, positive, positive, anything above that temperature, the reaction is going to be spontaneous. And anything below that temperature, the reaction is not going to be spontaneous. So that's when delta G equals 0. So what we're going to do is plug in our delta H, our delta S, and our delta G, knowing we want to set delta G equals 0, and we want to solve for a temperature. So again, we're using this equation, and we're knowing that the temperature tipping point, and that's the temperature we're looking for here, is when delta G equals 0. So we'll plug in a 0. Notice again, I converted my delta H to joules, and I kept my delta S in joules, and I'm solving for T. So when you come here when you solve for T here, T comes out to be 452 Kelvin, okay? And that's our temperature tipping point. So anything above that temperature, the reaction is spontaneous. Anything below that temperature, the reaction is not spontaneous. Now understand why that is, okay? It's because it was a positive positive combo. If this were a negative negative combo, then this temperature would represent anything above it becomes not spontaneous, and anything below it, it becomes spontaneous. Okay? So this is the temperature tipping point for this combination of delta H and delta S. But when they're positive, it's anything above this temperature, it's spontaneous, and anything below this temperature, it's not spontaneous. And then if they were negative, it would be the other way around. Anything above this temperature, it's not spontaneous, delta G would be positive, and anything below this temperature, delta G would be negative, so it would be spontaneous. Okay. All right. So moving forward. Okay. Oops. All right. Number 8. The free energy change for a given reaction is negative 36.2 kilojoules. What is the equilibrium constant at 298 Kelvin? Okay. So this is when we're going to be using this equation. All right. All right. So remember, free energy is delta G. So just in case you weren't understanding what the free energy chain was, it's just calculate the delta G, and they say calculate the equilibrium constant, and they give us the delta G. So the first thing to understand is delta G was negative in this question. So that means the equilibrium constant has to be greater than 1. So the really only answer choice, well, there's really 3 answer choices we can cross out, but the one we can definitely cross out is the one where the equilibrium constant is less than 1. So it can't be choice D, okay? It's probably going to be B or E because with this low of a delta G, any kilojoules negative, it's probably going to be a very... Oh, wait, you can cross out A too. Sorry, didn't realize A was less than 1, but A is less than 1. So D and A, you can cross out. Now 1.01, that's very close to 1. And so if this number were a lot closer to 0, then maybe choice C would make sense. But since it's such a low delta G value, it's probably going to be a pretty large equilibrium constant. So that's probably B or E are most likely here. But we can plug it in and solve to this equation. So we have this equation. It's on our formula sheet. All right. But we're solving for K. So we got to get rid of that natural log. So this is the same equation, just solved for the equilibrium constant. So E raised to the delta G over negative RT. And just make sure that when you plug in a delta G, you plug in joules in this, because remember, your R value that's given to you on your formula sheet is in joules. So whenever you plug in a delta G into this equation, it's got to be joules, not kilojoules. And then the temperature has to be on the Kelvin scale. So I forgot, was it? Yeah, they gave it to us on a Kelvin scale, but the main thing would be make sure you change that to joules and not kilojoules. All right, and then we just E raised to whatever that number comes out to be, and it comes out to be 2.2 times 10 to the 6th. Okay, but make sure, if you're practicing, have your calculator out and make sure you can plug in these numbers and get this answer. Because if you're not, You're just probably entering it in the calculator incorrectly. So what I tend to do is I usually just figure out what this ratio is. So I do negative this over this, and I figure out what that is, and then I do e raised to that answer. That's the way I tend to push the buttons in the calculator. All right. All right. So number 9, given the following information, calculate the delta G. All right. So we have the delta H and the delta S, and we have the temperature, and so we're just calculating the delta G. So we're plugging in everything into this equation, but just remember, we got to make sure our units are good to go. It's in kilojoules. I converted it to joules. So when you plug in everything into this equation, you get 13,400 joules, but divide that by 1,000 to get the kilojoules. So the answer comes out to be C. Okay. All right, so here we got to do a little bit more. All right, so if I go back to, so we're given molar heats of formation, or delta H's of formation. We're also given entropies, values of everything. Notice we weren't given the molar heat of formation of oxygen, and that's because it's an element. So molar heats of formations of elements are 0, so you don't need it, okay? But we're going to use 3 equations here, okay? And they're on our formula sheet. We're going to use this equation to figure out the delta S of the reaction. We're going to use this equation to figure out the delta H of the reaction. And then once we have the delta S and the delta H, we're going to plug those in along with the Kelvin temperature into this equation and solve for delta G. All right. So it's just using all of our equations on the formula sheet. So we got to calculate the delta H first, the delta S first, and then the delta G. So plugging in the delta H, and again, it's products minus reactants, and you have to also multiply by the coefficients. So that's where those 2's are coming from. We go to our balanced equation. 2 hydrogen peroxides, 2 waters, right? The 0 was the oxygen. You don't need to show that, but that's the oxygen, okay? So this is the delta H of the reaction, but remember it's kilojoules. When we do the same thing with the entropy values given, and again, we also have to multiply by the coefficients, notice that was in joules, okay? And then we're gonna take our delta H value, plug it in. We're going to take our delta S value, plug it in. Notice I converted to joules. You could convert this to kilojoules. I converted this to joules before I plugged it in. It still has its negative sign, right? So you're not changing the sign. You're just changing, from negative that many kilojoules to negative that many joules. But notice I didn't use 25 degrees Celsius. I used 298 Kelvin. And then I got this delta G. I divided it by 1,000 to make it kilojoules. Okay. Probably makes more sense to keep everything kilojoules because all the answer choices for delta G was kilojoules, but just make sure you're paying attention to the units and that they're in agreement before you add. You can't add kilojoules to joules. You can add joules to joules, you can add kilojoules to kilojoules, but you can't add kilojoules to joules, all right? And so when we do that, the answer comes out to be C. So since it was negative, it's the reaction is spontaneous, so thermodynamically favored. The equilibrium constant would be really big, a lot bigger than 1 there. And if you're asked about the cell potential, it's going to be positive. Okay. Yeah. All right. So as we go to number 11, predict the signs of everything. So just real quick, gas to solid, that has to be a negative delta S. So we know C, D, and E can't be, right? Okay. Sorry, not solid to gas. I think I said that wrong. Gas to solid. So that's a decrease in entropy. So we know it has to be A or B. Anytime this would be deposition, the opposite of sublimation. So deposition. Deposition is exothermic. Freezing is exothermic. Condensing is exothermic. So deposition is exothermic. So in order for this to happen, the particles have to lose energy, right? Gas to solid. So we know it's exothermic. All right. So again, that is still A or B. Now the question is, what's favored at room temperature, solid iodine or gaseous iodine? And you should know that iodine is a solid at standard conditions. So it's favored, so that means delta G is negative. So 11 would be, they're all negative here. Okay. If iodine was a gas at standard conditions, then it would still be negative negative for the delta H and the delta S, but the delta G would be positive, all right? Because it wouldn't be favored. But since solid iodine is favored at standard conditions, that's favored. Okay, so negative delta G. All right. Number 12. I think, do I say anything? Yeah, okay. So number 12. If a process is exothermic, so negative, that means negative delta H, okay, and it's not spontaneous, that means negative delta S, right? Remember, if you have a negative delta H and a positive delta S, the reaction's always spontaneous no matter what. Delta G will always be negative. So if you have a negative delta H, but delta G is positive, the only way it could be positive is if delta S was negative, okay? Right? So a negative delta H means it's favored in terms of enthalpy. It's enthalpically favored. And so if it had a positive delta S and it was also entropically favored, then that means delta G would always be negative and the reaction would always be favored. But you're told it's not favored. So the only way an exothermic reaction could ever not be favored is if it has a decrease in entropy. So delta S must be negative. All right, so for any reaction at equilibrium, which the following is true, delta G is 0, okay? KQ is the equilibrium constant 1, delta G is 0, and cell potential would be also 0 if you needed to know anything about that, right? All the following have delta G's of formations of 0 except. So elements have delta G's of formations as long as they're in their correct state of matter at standard conditions. So oxygen is a gas, so that would be standard conditions, delta G0. H2 is a gas at standard conditions. Calcium is a metal, it's a solid at standard conditions. Mercury is the one liquid metal that's a liquid at standard conditions, so delta G formation is 0. Remember, bromine's the other liquid of the periodic table. There's 2 liquids on the periodic table, 2 elemental liquids, and it's mercury and bromine. So Br2 liquid would have a delta G formation of 0, but not Br2 gas. Okay. All right. So I think, yeah, okay. Number 15. All right. So the last one. Ammonium nitrate spontaneously, so delta G is negative, dissolves in water at room temperature, and the process causes the solution to become quite cold. So if the solution's becoming cold, that means it's absorbing energy from the it's absorbing energy from the surroundings. The reaction is, so positive delta H. So we're already, just based on the information given, if the reaction became hot, negative delta H, it's releasing energy. If the reaction becomes cold, that means it's absorbing energy. Okay? So positive delta H, and because it was spontaneous, negative delta G. So that must mean delta S is positive, because the only time you could have an endothermic reaction that is also spontaneous is if it's driven because of entropy change. So that means a positive delta S. Okay. So the process is not exothermic. We just eliminated that based on the fact that we know it's a positive delta H. Delta S can't be negative. It has to be positive, so it can't be C. It has nothing to do with supersaturated solutions, and it doesn't mean they get cold. It means as the solutions are made, they get cold, but they don't stay cold. It just means it's an endothermic process. So its solubility will get warmer, or get greater in warmer water. Yeah. So this is maybe a Le Chatelier's principle thing. For any endothermic reaction, if you add heat, the forward reaction shifts right? The forward reaction becomes more favored. So because this process is endothermic, at higher temperatures, it's going to become more favored. So the solubility, it'll dissolve more at higher temperatures. And so B would be the right answer there. Okay. All right. Endothermic processes become more favorable at higher temperatures. Right. If this had been exothermic, then it would become less favorable at high temperature. Okay. Alrighty. All right. So again, yeah, it's kind of a longer video, but just going over that quiz and kind of detailed explanations for each answer. So I hope that helps you prepare for your thermodynamics quiz.